Great. So the last talk of the session will be given by Kengo Hirata on untangling quantum computing with separation logic.
Does it work? Okay. Yep. So hi. So this talk is about separation logic for quantum computing that can handle entanglement and measurement in a nice way. So why do you care about separation logic in quantum computing? Well, it's because in classical separation logic, it's been widely studied, and it's been shown that it can bring a huge benefit in scalability by enabling a modular reasoning for it. And we want to have a similar effect for quantum computing, so we want to do this. So this is a slide for a quick overview of our work. So before our work, there were some quantum separation logic existing, and they have been inspired by the classical separation logic, and they have introduced frame rule that can represent that enables kind of local reasoning for each disentanglement component. So this is inspired by classical separation logic, but we want to have like more like rich thing because like quantum computing is more complicated, and we have a lot of phenomena that doesn't occur in classical setting. We want to have some more rich thing, and that's our work. Oops. So the first idea we want to do is that we want to have a reasoning rule that can represent that correspond with superposition. That's the first idea, but it turns out this idea is, in a naive sense, is not compatible with measurement. So we're going to, but we still want to have measurement, so we're going to add something more that can to enable to reason about measurement as well. So that's the big picture of this talk. Okay, let me review the previous work. So in previous work, quantum separation logic, so separation logic is just kind of program logic. So there, a proposition represents a kind of quantum state. So for example, if you write like x maps to 1, that represents qubit x has state 1. And if you write like in the second line, then this can represent a state of qubits, state of qubits that has the state 1, 0. And we also have Hoare triple, and meaning if you have a precondition, and if you evaluate this NOT gate, then you get this state. And the motivating observation to introduce separation logic is this. So let's say you're given a quantum circuit, which is possibly huge, but let's say you manage to prove the first line. And then later, you realize that you also want to have the second line, which says you also have another qubit y, but this is disentangled. And yeah, let's say you want to have this one. And the first one, it's a way to just prove this is just do the proof again. But you don't actually have to do it because this should follow automatically. And that's the idea of introducing separation logic. And we want to represent this phenomenon logically. So to do this, separation logic introduces something called separating conjunction that can represent a disentangled state. And with this thing, for example, if you write like psi separating conjunction phi, then this will represent disentangled state like this. And to realize this reasoning, they introduced frame rule. And for example, we can do the same thing as we wanted to do. And the intuitive meaning of this is like, if you want to prove the second line, then you can focus on some disentangled resource, which is local, and then just prove that up, then add the disentangled state later, and to prove this second line. So this is some kind of reasoning rule that allows you to focus on some disentangled component. So I want to call it entanglement-local reasoning. So this is cool, and it works. But the question I want to ask here is this really enough to achieve some kind of modular reasoning in quantum computing? So here I want to see the second observation. So let's say you now have a unitary circuit, and then you have proven this two specification, which says if the input is 0, 0 or 1, 1, then it behaves like identity. Now the question we want to ask is, what if we have another qubit which is entangled in this case. So here, entangled means like you cannot separate the state of x and y as a tensor product. But because, as I said, this is unitary and it's linear, so you should be able to derive that it also behaves like identity in this case. However, frame rule doesn't allow it to like derive this immediately because frame rule was only for disentangled resource. So that sounds like a limitation. We want to have something more. And the idea is, in our work, is just to add a linear algebraic structure for propositions. So what we introduced in our logic is that first we add a scalar multiplication for proposition and sum for propositions. And each of them correspond with usual vector calculus of them. And we also have a corresponding derivation rule for this. The first one says if you have a Hort triple, you can you can multiply some scalar to derive another one. Or the second one says if you have derived two Hort triples, you can just take the sum to derive another one. And this solves the problem. So let's see how it works. So this was an assumption. Now, with the frame rule, you can add another qubit. In this case, this is disentangled, so this is allowed. Now you can add a scalar to derive this. You can do the same game for the case of 1. And you can finally take the sum to derive the thing you want to have. So it works. Let me explain our idea in a little bit different perspective. So I want to make a claim here, which says this idea of adding scalar and sum bridges some kind of gap between intuitive proof and formal proofs in certain sense. So the question I want to think here is that, so let's say we're given some kind of circuit, and we want to check this implements some kind of unitary U. And intuitively, what people usually do is that they say, it suffices to check the finite case of the basis case to prove this, and that is enough because of linearity. And in our logic, we can do the similar thing. So what we can do is that we can just check the Hort triple for these cases, and then finally, by using the scalar rule and sum rule, you can derive the thing we wanted to have. So because this reduces the problem into some basis, we want to call it basis-locality. So that's the idea. Well, that's very simple, and probably too simple. And you might be wondering, why is that new, and isn't there any problem? Yes, there's actually a problem. So it's measurement. So measurement is problematic. Because let's say now a program we're given is measurement, then because measurement doesn't do anything for the computational basis, you should be able to derive these two things. But by using scalar rule and sum rule, you'll be allowed to derive this, which says this measurement is equivalent to identity, which is completely wrong. So this is problematic. What's the problem? It's because measurement is not linear in this sense. Okay, we want to solve this problem. The idea to solve problem is that we want to be a little bit more precise in the post condition. So let's think about this Hort triple, which says you want to measure something. And the post condition I want to consider here is that something like this, which says after measurement, you create some kind of branching. And if you branch it to this side, you get ket 0. If you branch it to the other side, you get ket 1. And what is good about this idea is that if the input is linear combination, the output is going to be linear combination as well. And why is this true? It's because simply measurement is linear with respect to each branch. So let me formalize this idea in a logic. To do it, we're going to introduce another combinator, which we call mixing. And with this notation, so we use O+ notation with superscript that represents kind of ID for branching. And now with this combinator, we have this rule, which says if you measure ket 0, then you get ket 0 or some kind of state that never happens. And never happens is equivalent to say the probability is 0. if you measure ket1, you get something similar, but on the other way around. And with these two rules, we can now safely use the sum rule and scalar rule to derive this one. And from here, I can just distribute this scalar like this. And then finally, we can take the sum. But here, when we take in the sum, we just add the left-hand side with left-hand side and right-hand side with right-hand side. And then now we can get this one, which is correct because this is not anymore saying this is identity, but rather saying like you can get two results. And corresponding to this mixing operator, we also have a rule for this, which allows you to combine two Hort triples by the mixings. And we want to call it outcome-locality. So far, I have presented three localities, each corresponding to separating conjunction, sum, and mixing. And this is the core idea of our work. Okay, and corresponding to the new connectives we have introduced, we have in our paper we presented a lot of like new rules that is useful for reasoning. I don't have time to like explain everything, but if you're interested, I want you to take a look at our paper. But one thing I want to note here is that in some of the rules, if you want to prove left side from the right, it requires some kind of side condition. And I want to call this, I will call this side condition as frameability. And frameable propositions are some kind of nice propositions. And roughly speaking, these are the propositions that is constructed without using disjunction. And so, for example, every atomic formulas are frameable. And also, frameability goes under conjunction, separating conjunction, or sum or mixings. So in practice, a lot of propositions are actually frameable. OK, so in the rest of my talk, I want to talk about some kind of trade-off happening regarding the measurements. And also, I want to show how our logic actually scale in practice. One thing I haven't talked about is global phase. So what is global phase? Those are just a complex coefficient for a vector. And it is known that physically, these are not observable, meaning that this, for example, like ket1 or minus ket1 or I ket1 are observably equivalent. So we usually identify these three states. But however, in our logic, we cannot ignore these things. Why? It's because if we allow to ignore these things, that means we treat these propositions as an equivalence proposition. But because we have some rule, this allows you to identify these two things, which is completely different. So we're not allowed to do this. That means our logic is actually based on vectors rather than density matrices, because density matrices allows you to ignore the global phases. But however, like usual, like most of the existing quantum Hort logics are based on density matrices because it's more natural to represent the measurement outcome with density matrices. And actually, there's kind of trade-off happening here. As I said, we wanted to have basis locality and sum. We had to use vectors. However, to represent the measurement outcome, in our logic, actually, in some cases, some kind of blow-up can happen for the outcome of the measurements. And more concretely, so let me introduce another notation of big O+, which just represents the O+. And after n measurements, you get n branching. That means you have 2 to the power n propositions combined with O+. And this is actually blowing up. And indeed, actually, blow-up is sometimes unavoidable. So sometimes you might need to give up basis locality or scalability of size. That's actually true. However, what I want to say here is that in our paper, we presented a lot of case studies. And in those case studies, you can actually avoid this blow up, even though there are some measurements happening there, by doing some kind of smart way. So let me give an example for this. So the example I want to show here is this circuit, which is the error correction circuit for the bit flip code. I don't want to explain about the detail. You don't need to understand it. But one thing I want to mention here is that there are two measurements happening here. And so to verify some big circuit, or I mean, it doesn't need to be big, but to verify something, because of basis locality, you can reduce a problem into classical inputs. And now, because this circuit looks like classical circuit, if the input is also classical, you can easily derive this. So this is very easy. You don't need to understand a precondition or a postcondition, but yeah, this step is trivial. And one thing I want to focus here is that this part doesn't depend on the O+. And because of this, we can use the distributivity of O+ and separating conjunction. And by using it, we can put this last part to the front and leave the O+ to the rest. And what is important here is that because the rest part is not important, we can just forget it. Now, in this postcondition, we have existing quantifier for some favorable proposition, but there's no O+ appearing here. And we have proven this. And from this, we can just use scalar rule and sum rule to derive the thing we want to have. And one thing I want to note here is that I didn't mention, but frameability of P is actually used effectively here, so it's actually important. Yep, in our paper, we have presented a lot of other case studies, including algorithm which uses dirty qubits or quantum teleportation, and implementation of CNOT gate with 2-qubit measurements, which is the technique used in ladder surgery. And the next thing is something I just presented, and we also can also verify the correctness of short codes error correction. So this is a slide for related work. So the first line, Zhou et al. LIX 21 paper has introduced the quantum separation logic. And in the second line, POPL'26 paper added the classical variable treatment to it. And the next paper introduced kind of precise reasoning for probabilistic outcome to it. And our paper introduced basis locality to it. There's another quantum separation logic from Su et al., which is also a separation logic, but this treatment of separating conjunction is a bit different, so it's a bit hard to compare. Right, so this is the slide for conclusion. In our paper, we have introduced a new logic, which we call RapunSL, and we have separating conjunction and sum and O+, and corresponding to these three things, we have a locality. And in our paper, we present a lot of practical case studies. And as a future work, we're considering extending to some relational logic, or we're also interested in automation. And also, I'm personally interested in adding concurrency or non-determinism to it. So, yep, this is the end of my talk. Thank you for listening. I want to have questions now.
Thank you. Questions?
Hi, thank you for the talk. So is there a way you can generalize this to generic superoperators? Like you gave a way you can do for measurement. So if you were considering the superoperators, which is like a general quantum channel, can you extend this logic to that?
I haven't considered about it, maybe my answer is I don't know, but maybe interesting way to go on. Yeah, we can discuss later. Yeah, that sounds interesting. Thank you.
A clarification question. The plus for linear combination and the O plus for a mixture has very similar rules. Are there distinction like more logical in the sense that you want to distinguish mixture to handle the case, the difficulty for measurement, or is the physics also different?
You mean, are you asking the difference between plus and O plus?
Yeah,
Is
yeah.
that the thing?
Like, is there a difference in the physical world, or
Yeah,
did you
it
introduce the distinction for the logic to work?
Yeah, so plus is for superposition, which is, I don't know, it's a kind of, it's not a probabilistic difference, but O plus is the probabilistic mixture, which is some kind of classical superposition.
Okay, okay.
Yeah.
Sounds good.
Thank you.
I think there was another, yeah.
Okay, thank you for your clear talk. It's a great work. But to me, it seems it's more like symbolic execution on pure states. Do you think so?
Yeah, I mean, yes.
And you discovered a clever way to reason about it locally.
Yeah, I mean, yes, that's exactly how I see this, especially for this case study. So I didn't explain anything about something that happened from here to here, but to derive this one from here, we just do the symbolic execution. And after doing it, in our logic, we can just generalize the input. So it's like a combination of symbolic execution and generalization to the every input. So I mean, I see the very relation between it.
So actually, my question is, in whole logic, we talk about predicates because we don't talk about individual states. So what do you think is the predicate here? What is the difference between predicate and state? And what is your language for the predicate?
So I probably didn't understand what you mean by predicate. I don't understand the difference between the
in the
predicate
classical
and state.
case, we don't reason about the classical program state directly. We reason about logic formulas, right?
But I think, I don't know, yeah, we can discuss later, but yeah.
And also, it's about pure states, but in quantum algorithms, we always talk about probabilities.
Yeah.
So, are you considering extending this work to use density operator as the predicates or states?
So, as I explained, our logic is based on vector states, but with this mixing of us, you can represent mixed state, not in the way people usually represent in the density matrices. If you use density matrices, we lose basis locality, but that's the thing we wanted to have. But we still can represent, represent some kind of density matrix in our logic as well. So we're not giving up some representation of probabilistic mixture of it. Does it make sense?
Yeah, thank you.
Yeah, thank you very much.
Other questions? Thank you for the talk. So I'm wondering about the scalability. I understand that all your case studies were done manually, right? Is it so?
Yeah, that's true.
And the examples that you show, it seems like very simple circuits, maybe 5-6 gates. So how about if you go for something bigger? Do you have some bounds on the size of the proof, for example?
The biggest example we have proven is this one, which uses this one as a building block. And, well, essentially it's not big. It's not very big. I don't know how does it scale for the very huge one. That's kind of like a future work for us.
And the size of the proof, so is it somehow related to the gates, or how would you describe the size of the proof, for example?
Size of the proof? I don't know. I mean, the general idea is just like a symbolic execution here. So for each gate, we have one line for whole triple.
Yeah, but I mean, like the size of the lines can grow, right? So.
Yusuke, do you want to say something?
So I'd like to add that, like, because we're using logic, we can do some kind of more like clever things. And as for the show code case study, as Kengo mentioned, like we use error-free code as a building block, and we can reuse the result like 3 times. So like in that sense, we don't need to like kind of actually simulate everything, but we can do like more clever replication of the existing results.
Maybe if there is one last short question, otherwise we can thank the speaker.